great pleasure to have Ilyes Batatia, if I've said that correctly, from the Shiny Group in Cambridge, along with Venkat Kapil here, who are going to try and give an introduction to the basics behind the MACE model that's grown hugely in popularity in the last few years, general machine learned interatomic potentials, and some of the practical applications of using these on young and other HPC workflows for their use in materials and molecular modeling. It's really an essential component in the armory of atomistic modeling these days, and so it's important that people know how to use them effectively. So, without further ado, great pleasure to introduce Ilyes to kick off this software spotlight. Thank you.
Thank you very much, George, and thanks, Venkat, for splitting this talk. So I'm going to start with basically a bit of basics on machine learning potentials, and I will be focusing a bit more on MACE. Um, so just one second, I just want to make sure I don't go over time. So uh, okay, so basically the goal is to our goal is to scale up computational chemistry, and I always like to show this plot that basically shows the size of the simulation you can do to simulate matter in the number of atoms in the x-axis and the the accuracy that you can get out of this simulation. And on this corner here, you have the very accurate, close to exact quantum chemistry methods, and then on the right, you go all the way to things that can simulate billions of atoms, but at accuracies that are mostly only qualitative. And there is a huge market for being able to simulate a bit more than 1,000 to 10,000 atoms, but with accuracy that is close to DFT, which is the bug standard for doing ab initio simulations now. And this is exactly what machine learning force will try to do. In most cases, they try to learn the DFT and be able to reproduce it. But instead of being contained at a few hundred of atoms, they want to scale it to 1,000 to 10,000 atoms. And this is extremely significant because if you look at the use of the UK cluster, this is the Archer CPU cluster in 2021, and it's the same in the last few years. It's mostly dominated by simulations trying to basically do one of the methods that I've showed earlier. And in particular, about 60% of the whole cluster is used to do either DFT or semi-empirical methods or quantum chemistry methods. So, and this is over all the scientific usage of the cluster. So being able to speed that up is very important. And the reason why everyone is doing that is because these simulations are a necessary component to understand anything at the atomic scale. And the reason why we believe that it's possible to speed up these things is because if you look at how you do these simulations, so mostly molecular dynamic simulations at the ab initio level, you will have to solve this Schrödinger equation, which is a partial differential equation. And the solution of that are these wave functions. And these are very high dimensional objects. And depending on the approximations you do on this H here, this can be somewhat extremely expensive to compute this full solution. But when you are doing the molecular dynamic, actually you just throw this solution to the bin, and you only keep a sort of classical average of this solution, which is these forces here, which are sort of classical uh, um, which are analogous to the classical forces on the Newton dynamic, and then you use these forces to evolve the position of the atoms. So these forces are inherently quantum, and they are computed downstream from the wave function. But in the end, you only care about the forces, and you don't care about the wave function. So can you just shortcut that? And actually, uh, quantum chemists have been able to shortcut that for a very long time now for simple systems. So you basically have to parameterize a function from the positions of the atoms, which is this R3n, to just a scalar quantity that are these energies, and then you can differentiate that to get the forces. And in very simple system, you can actually derive analytical form for these potentials. And quantum chemists have been doing that for over 50 or more years. And the idea is how can you scale that up to much more complex system where analytical solutions might not be available. And the dream is to be able to basically use such potential to do simulations like this small battery at accuracies that are of the order of the DFT. So really the quantum accuracy. And how you go about doing that? Well, you need a way to parameterize the energy of your system, and this is exactly what we do. And I will go about all the usual systematic approximation that we do to make that more tractable. And this is mostly shared by all different kind of machine learning potential. So we are trying to learn basically the energy of the system, which is a function of the position, which are these R, so the position of all the atoms, and also the atomic species exists Z, so whether it's hydrogen, oxygen, etc. So you see here, there are no electrons anymore. So we have coarse grained all of the electrons. And this is the big gain. And the only electronic structure that is in this function is in this Z. So you only look at a sort of coarse grain representation of the electronic structure with these chemical elements. And one approximation that we do right off the bat is to assume some kind of locality. So we are going to want to simulate systems that are much larger than what we can train on. So locality is a very big proxy to be able to do that. And this means that first we decompose the energy as a sum of site energies. So each atom has its own energy. And then we assume some locality, which is the energy of the atom I is only a function of the neighborhood. Any atoms that are within a certain distance of I will interact with it. We also usually, and this is debatable for some people in the community, try to enforce some symmetries that are from the physics on this function. So it should be invariant to rotations, permutations, and translation of the whole system. And then one extra useful approximation is to do a sort of body order expansion. So we try to expand these site energies as a sum of one body, two body, and three body terms, and try to approximate each of that. So here I just made a graphical illustration, and this is quite common in the classical force field literature. And some of the ML potentials all have in some form a sort of body ordering, even if it's in reality it's a bit it's not strict. Um, and if you go about this body ordering, you might want to say, okay, the most naive way to build your model is to find a basis for every of these V functions. So a basis for the two body, a basis for the three body functions, and then just learn a linear combination of it. And this is like the most naive way. So how you could do that? Well, you could do the usual quantum chemistry things. You take a one particle basis, which is just a product of the radial components, so just the distances, and an angular component that you expand in spherical harmonics, the well-known spherical harmonics, and then you just take a tensor product of these, and you can show that if you take sufficient tensor product of these, well, you can approximate any of these order function by taking sufficiently high tensor products. But the problem of that is that it doesn't follow two of the key properties that we would like. First, it's not invariant to permutation and rotations. You don't have any the final basis is not symmetrized, and that also when you scale the body order, it scales exponentially. So you cannot go very high in the body order. And just to give an idea, things a model like Maze today to be the most accurate has to go to body order 14 or 13. And here it would just not be possible here. So the whole goal basically, as I see it, of the field is to find a way to efficiently sparsify this basis. So pick only the elements that are the most useful for regressing the potential energy surface of a system. And MACE is one such specification. It's what we call a many-body equivalent message passing neural networks, and I will go in detail about each of these words. So a message passing neural network is basically a neural network that operates on graphs. And it maps a label graph, so a graph here that I've shown like a simple graph, and each node of this graph has a label, this sigma, which I call the state. and you map that to a scalar quantity, so which is the energy. And the state, in our case, is basically describing all of the information that we need for a given atom. So its position, so this is just a vector x, y, z, some set of fixed attributes. So usually this is just the chemical element, but it could be also the spin or the charge or anything you like. And then a learnable feature, which is a sort of extra parameter here that we initialize just to be the chemical element, but that will be updated with learnable function of the environment of the atom. So this is really what will then be used to read out the energy. And I call that a semi-local state because MPNNs are iterative methods, and the more you iterate them, the bigger the receptive field of your method gets. So if you iterate like 5 to 6 times, like some of the models do, you end up having a semi-local state that is a function of 60 angstrom atoms within a 60 atom cutoff, which is much larger than what you would call a local model. Uh, MACE usually only has a receptive field of about 12 angstrom, which is mostly in the, I would say, still reasonable for a local model, and most classical force fields have this receptive field. Um, so what are the phases of, of MPNNs, message passing neural networks? They all share three phases. The first one is the message construction phase, which basically embed the state of two atoms that are on a bond. So you take a bond, and then you have I and J, which are the states on the bond, and then you need to embed it with a function M. I will say later what is M for MACE. And then you get an embedding of the bond, and then you gather that over all of your neighbors. So you look at all the information of your neighbors, which is the set Ni, and you gather it. So this big plus is usually just sum, but actually it can be any permutation invariant operation. And after that, you have gathered all the information of your neighbors into a message, mi. So this message is really, if I'm sitting on a hydrogen somewhere, I've looked at every information that I have of my atomic neighbors around like 6 angstrom, and I've gathered that, and then I've gathered this in a collected invariant message. And then I use this message to update my state. So I'm the atom I, and now my new state is also a function of what my neighbor is. So if I'm a hydrogen with three oxygen in 6 fraction cutoff, I will be different if I'm than if I'm a hydrogen with two oxygen in the neighborhood. So then this new state is strictly richer, and this is done by an update function. And then after you've done that t times, you read out the energy by just mapping the state to a scalar function, this EI. So this is common for all MPNNs. And one extra subtlety is that MACE is an equivariant MPNN to the O3 group, which means that the internal feature of the neural network, I have a defined transformation under the rotation. So if you take a rotation Q and then you rotate your input, so your molecule, and then you look at the internal features of the model, it will not change randomly based on the rotation that you do. It will change in a linear way, actually, which are given by these Wigner D matrices, which are the irreducible representation of the O3 group. And to give a visual representation of that, let's say L is 1, and then this feature will be an internal vector. And if you rotate your input like this water cluster here, then your feature will rotate with it. So it has a prescribed way. And actually, we have also higher order vectors and obviously scalars, and we are using the spherical harmonics basis to easily keep track of them. So what were the limitation of MPNNs before MACE? So the first one was that all MPNNs were, at least all the equivalent MPNNs, were passing only two-body messages, which means that at every layer you could only pass functions that are just a sum of two-body functions. And this strictly limits the expressivity of the model if you do few layers, because we know that the real potential surface is very high by the order. And it creates a very a deep relationship between the number of layers of your network and the expressivity, because the only way to build up the body order is to increase the number of layers, but that also increases the receptive field. So you end up just increasing a lot the receptive field, while the only thing you want to do is actually increase the body order. So it's a severe limitation. And if you want, the other people that tried to do many body message passing networks, they all use only angle-based many body features, which are based on triplets or quadruplets of atoms, and these also scale very bad, especially with the number of with the body order that you use. So it's actually it starts to be already limited at quadruplets, and you cannot go higher. So MACE is a MPNN architecture that basically does equivariant high body order feature in an efficient manner. And we usually use four body messages and just two layers, and basically reach state of the art like that. So just a bit of more detail on how you do that. Basically, the idea is to take the message and then expand it again into a sort of Taylor expansion as a function of states of your neighbors. So this is a function of the two states, and if you were to do a traditional NPNN, you would just stop here. But here you also have other contributions. And the idea is to use a sort of modify a basis, which called the tensor modify because it's what we call the tensor reduced A basis, and use a linear combination of these to approximate each of these terms, because this basis is a complete basis of many-body equivalent features. The way you go about constructing that is that you first construct a two-body a feature, this A basis, which is simplified as just a product of the radial component, an angular component, and then an extra feature component, which basically is usually the usual equivalent feature of MPNNs. And this is only two-body. You make a tensor product, and then you gather over your neighborhood, and you see this is still two-body. So if you were to do a traditional MPNN, you will stop there. But MACE has an extra operation, which is this symmetric tensor product. And you take this A basis, I won't go in too much detail on the indices, but you take this A basis, and the central operation is that you take product of them. And the key thing is that because you have done the sum first and then you take the product, this now doesn't scale with the number of neighbors. So you end up being able to do very, very large body order without being hurt by the number of neighbors you have. And by taking the product of this permutation invariant to body. And then, so we have solved the first problem that I was saying to approximate tensor product basis. It's not scaling exponentially anymore. And then the second problem was the invariant to rotations. And this is done using these projection operators, which are the JRS Clebsch-Gordon that maps these tensor product features to the subspace of equivariant features. And then you end up with these B bases, which are a complete basis of many-body equivariant features, and you can just approximate your message by a linear combination of them, and then you get a message that is arbitrarily high order. So this is the central idea behind MACE. And after that, you get your message, which is now many-body, and you can update your features with an update function, which is usually just a linear function in MACE. And at the end, when you do that t times, and in MACE is only 2 times, you map the energy with a readout, and we use just a linear function for the first layer and then a nonlinear function for the last layer. And the important thing I want to say is that doing 2 layers of MPNN is different than doing a 2 times larger cutoff for a single layer model, and I will explain that. So if you take a sort of single layer models like ACE or Allegro, and you take a large cutoff, then you end up creating basis functions like that. So this red atom is a central atom, and it will have basis function describing these free body terms here, which seems sensible in the potential to contribute significantly to the potential surface of this molecule. But you also end up creating this basis function. And it's quite likely, if you are a chemist, that you think that this term is actually quite weak and could probably be ignored as an approximation. And if you actually do 2 layers of MPNN, then you can use a smaller cutoff here, and then you iterate it twice, and you see that this will create this free body feature here, and you still have this describe, but it will not create the extra feature there with this hydrogen. So really 2 times 4 angstrom is not the same as the 8 angstrom model. And this is giving a hint on what I was saying to as a sparsification of the full basis. It's really picking up the right basis function. It's actually a chemical way to do that. And the last thing I want to say on this is that we show that really the limitation of the other previous MPLNs like Nequip or Botnet were that they were using their stacking layers just to increase body order. So here it's a simple regression chain on a small molecule, and here you have the RMSE on the forces and energies, and you see that Maze can basically get saturated accuracy on just 2 layers, while the non-many-body equivalent message passing networks needs to stack layer. But obviously, at 5 layer, you have a receptive field that is much larger than the size of the molecule. So really, it's not about seeing further. It's just about increasing the body order. And now I want to talk about foundation models quickly, which are I think, one of the most exciting applications of these machine learning potentials today. And basically, really, they try to be a solution to one of the biggest problem of machine learning potentials today, which were this endless loop of retraining. So usually, anyone that has basically fitted the potentials in the last 10 years have suffered from that. You start with your initial database, and then you fit your potential, and you're all happy because, I mean, it took time to collect your initial database, and then you run molecular dynamics, and you have explosions like the one I show in this movie. Everything explodes. And then you're forced to basically take some frames of these explosions, redo some computations, add it to the database, and then try to redo dynamics. And then this time can take a lot of this loop can take a lot of human time to converge, and actually it takes usually years to have a stable potential. At least it used to take years. And the idea is, can you find a way to basically train on large enough data sets such that your model is out of the box stable and maybe even out of the box qualitatively accurate, such that you basically speed up a lot the development of any potential. And this is why I call it a foundation model. And one thing you have to think about when you try to fit on very large databases is you want to have a model that is out of the box usable for a lot of elements. And if you were to represent your elements in the network as a discrete quantity, then you see that, for example, with Maze that has 13 body basis function, you will have that size of the number of features of your network, which is much, much larger than you would like to code in your computer. And so one key thing that all of the potentials do today is to embed the species in a continuous space. And then actually you get a model that is constant in cost. And one remarkable thing I think of these models is that the final model that you need to use to fit 89 elements is actually not larger than one that you need for fitting one element. So really, there is a very, very compressed subspace as a function of element. And if you look at the embedding that these models learned, it's actually quite similar to the periodic table. Uh, so we went about fitting a maze model to all of the materials project, and we produced this MP0 model. Um, and then we tried to benchmark it as thoroughly as possible. So we started asking people around to test it on their favorite uh, um, system. So we tried zeolite, morphs, reactions, salt, interfaces, ice, all of these things. And then we made a comprehensive review on what worked, what failed, what was qualitatively or quantitatively accurate. And we compiled that in this large paper that is, I think, the most comprehensive benchmark of any of these models. And what we ended up being very surprised of is that it's actually a sensible model for a lot of things that are completely out of domain. So the training set is just the materials project, which are small inorganic crystals. And then we tried it on things that are much, much out of domain. And Uh, Basically, training on these data set, that is 89 element, that's PBE plus U, DFT, and it's only 1.5 million crystals, you can do things like amorphous carbon system, where here we benchmark the model on amorphous carbon against specialized, specifically trained for amorphous carbon models like here ACE and GAP that have seen 10 or 1,000 of amorphous system. And basically the model out of the box is as accurate on these basic properties, while having seen no amorphous system at all. It only has seen crystal. So it really has learned some kind of generalizable notion of chemistry inside. And this has been true for a lot of the system that I've shown in the previous figure. And so that's why I encourage you to go over the long appendix to see exactly the performances. So why are the foundation model exciting? So first of all, they are basically doing stable MD for a very large part of the chemical space. And this is very exciting because then you can just cut off the endless loop of having a stable potential and just go right through the science. And just to give an idea, I think a model that would have a potential that would have taken 2 or 3 years to be developed in a few years ago can now be developed in a few months. So it really has sped up a lot the field. And sometimes, and I would say even a lot of times, it has a good qualitative agreements with the underlying DFT, and sometimes it's even quantitatively true, accurate. So this is even more useful because you can get reasonable answers. And then the last point, which is I think the most important, and Venkat will go in more detail about that, is that they are very easy to fine tune. So even if they are just qualitatively accurate out of the box, you just need a few data to make them quantitatively accurate. And I think this is really the most exciting thing of this foundation model, and it's why I insist to call them foundation models and not universal potentials, because I think really fine-tuning will always be an important part of the use of these models. And the last point here is that the training set, the materials project training set is actually not very large, and it hints that there are large potentials for even better models. And I will go just quickly about sharing our latest results in improving these models. So right now you can just go into your notebook and install Maze, and then you can run MD basically for any system you want. And here, this is a surface with a lot of molecules on top, and it gives you pretty animations. You can even simulate the whole periodic table if you want, which is this fun animation here. And if you go for a long time, you actually see quite fun physics happening in these movies. So just a bit of um, explanation on what is fine tuning. The idea is that you take your foundation database, you train a foundation model, and then once you want to use it for producing real science, well, usually either the foundation model is not accurate enough to simulate your the thing you're interested in, or the DFT that you have used to produce the database is not accurate enough either. And because obviously you need a large database, so you cannot get large and accurate ones. So basically, you just compute a fine-tuning set on your system of like a few quantum high accuracy points, and then you just fine-tune, and you can right now fine-tune out of the box in Maze using this command line, and I will show how to do that in the tutorial for a few minutes later. So one thing that we try to solve the last few months is what are protocols that are good for fine-tuning. And I'm sure Venkat will also go in detail about that. I will just talk about the high level here. So what you want to have a good fine-tuning protocol is that you want to achieve good accuracy. So you don't want to underfit. You want to get to the correct accuracy. You want to keep robustness, because the big thing of this foundation models is that they were not exploding. So if now you fine-tune and they all explode, I mean, that's bad. And then you want to limit the cost of the fine-tuning. So you don't want the cost of the fine-tuning to be as costly as training the foundation model. So one approach that we've done for that is this multi-hide replay fine-tuning, where you take your pre-training set, you sample it with a sampling method, which is usually just random, but you can be more clever about it. And then you get a replay set, which is a portion of the pre-training set, and you get your fine-tuning set. And when you train, you both fine-tune on your new data, but you also keep replaying your pre-trained set. And this is what we call in continuous learning, in machine learning, a sort of experience replay where you learn new things, but you also try to not forget about the old things. And this has proven to be actually very useful. And we have I won't stay much on that for the sake of time, but we have made a lot of experiments on the MP0 paper on how accurate fine-tuning can get. And here, the blue dots are the training a model on for each of the system on top on a select few hundred configurations that we've reevaluated for this system with DFT. So this is what you will get if you train on from scratch. And then these um, uh, pale symbols here are the out-of-the-box accuracy of the foundation models. So you see that our MPA model, which is a new generation of foundation model, is on a lot of cases as accurate as training from scratch, even if it hasn't seen any of these systems. So you might just use it from scratch. And then if you use the data that you have generated to fine-tune it, then you see that you have a big improvement that is sometimes a factor of 4 to 5 depending on the system. Sometimes it's just a bit better. I mean, sometimes it's much better, and importantly, it's never worse. So basically, I would say right now you should just fine tune, and training from scratch is usually not useful except for validation purposes. Um, and the last thing I want to touch on is our effort to basically scale up this foundation model to larger and larger databases. And now we have trained models on databases that are about 200 times larger than the Materials project. And here you see the Materials project 1.5 million, and MPA was trained on 12 million. And then we have a model that was trained on 100 million. And we have no models that are trained on even larger datasets. So we have a collaboration with Meta that generated this huge molecular dataset of 100 million hybrid DFT calculations, and we have trained a new model that basically is pre-trained on OMAT and then fine-tuned on basically a lot of datasets, including surfaces, molecules, materials, reactions, and then we just use the one head of this multi-head architectures to be the final model, and then we've done a very extensive benchmark across a lot of properties, and you see that the model basically now can be out of the box accurate, not just for bulk system, but also on molecular crystal, surface, uh, and molecular systems. And we are getting closer and closer to have models that are out of the box, quantitatively accurate to a GGA functional. And I expect that in the next few years, we will have models that are basically PBE out of the box for most of chemistry. And the last thing is that the premise of these models were that they are accurate but also fast. And so it's very important to also speak about performances. And basically, I would say that right now you can do about a few nanoseconds a day, so a million step of MD per day for 1,000 to 10,000 atoms. And we have worked very hard, notably with Chuck, to basically have performance implementation of MACE. And this is a reimplementation of MACE in C++. And you can do both CPU and GPU, multi-GPU and multi-CPU evaluation. So you can parallelize using domain decomposition in your system. And you can scale now to even millions of atoms and still have, if you put enough resources, good performances. The other things that we have done is that we have a collaboration with NVIDIA to create custom CUDA kernels for MACE, and we've seen continuous improvement in speed of these models, and now this generation is about 6 to 7 times faster than the pure PyTorch model, and you can use also these kernels in lamps using the MLIP uh, um, um, interface, and you can also scale to many GPUs, and it's basically also a few nanoseconds per day, which I would say is roughly the standard now for the accurate potentials. and and then you have no independent software that also try to do these fast inference models. So this is dist ML IP, which is another one, and this is chemtrain deploy, and there are new frameworks that are appearing basically every month now. So it's a very active field to making these models faster and faster, and I expect that both the hardware and the architecture will basically make these models much faster in the next few years. So some of the limitation and outlook to finish the talk. Obviously, the first challenge of these models is actually electronic structure. So we have no universal functional, and this is why I think fine-tuning will be super important. So unless we have a universal functional, we cannot have a universal potential either. You always need to accommodate with the approximation of your underlying theory. We need to learn better how to fine-tune to higher level theories because of that. Um, Better coverage of the chemical space, and this is something we have worked on and new preprint will appear. It's very important to have automate suite of tests to validate these potentials because we are making big claims and we need to be backed up with also big evaluations. And we're also working on that to be able to steer the field in the right direction. And obviously, the locality approximation that I was talking about at the very beginning of the talk is actually breaking down on some cases. So whether it be dispersion interaction or electrostatic interaction, and we have new models now that include these long-range interactions in a physical way in the model. So all of these things are what we are working on right now. Um, so this was the end of the talk, and you can go see the code, the Maze code, which is open source here, and then the models that we always upload at this link, and we are keeping uh, improving them. So it's a quite a fast-paced field, so you will see a lot of new models coming out. Um, so then I think I can switch. Maybe if you have questions, you can ask them now. But I can also switch quickly for like a very quick tutorial just to see how you can run some maze code and some fine tuning. Uh, I see that there are some questions in the chat. When fine, I'm reading them on cloud now. So when fine-tuning with a replay plus fine-tune mixed approach, can you generate the replay dataset directly from Maze model, or do you need to have access to the original training set? So that's a great question. Actually, just now in the latest develop branch, I've merged a way to do the replay with the Maze model, so you don't need to access the original training set. And the way you do that is that you take, usually we have a standard part of the materials project, you reevaluate your foundation model on it, and then you use the replay to be the energies and forces labeled by your foundation model. So you are really replaying your own predictions. And this actually has proven to be quite useful. And I will be in the next version of Maze, this will be the standard way to do the replay fine tuning. So I write some documentation. If you want early access, you can use the develop branch for that. And then Charlie said, would it possible to pull all the graph node embedding first to send out the readout phase if the property we're trying to fix predict cannot be broken down for an atom by atom basis? For example, I wanted to build a binary classificator using Maze architecture. So yes, it's possible. So you can make a sort of global readout. For example, we've used that to predict the band gap of properties. And usually you would need to have an aggregation phase. And what I recommend you to look at is this kind of spectral aggregation, where you do mean pooling, average pooling, all of kind of poolings, and then you use a small transformer on top of these pooled maze features to regress your quantities if it's not an atom by atom quantity. So this has proven to be quite useful, and I might be able to share some code if you email me, Charlie. I can drop some code to do that. And then uh, is the foundation model trained on open shell or shard structure? So right now, the Mace MP0 and MPA and OMAT, all of these ones are trained on closed shell neutral systems, periodic ones. But I've just dropped an OMOL model that is trained on the OMOL with all of the charges and spin states that you can download in this repo. And then you can also evaluate OpenShell or charge structures. And we are going in the next few weeks to release a new electrostatic foundation model trained on OMOL that can do um, long range dynamics for charge structures. So yeah, stay tuned. I will probably upload it just there. So if you keep track of this repo, then uh, you will have a notification for that. So if this is all the questions, and you can obviously, I encourage you to. We have a very active. So I actually let me share a new screen now. Uh, I will share this screen. Yes. Uh, well, actually, no, not this one for now. Sorry, yeah, this screen. So if you see my screen now, this is the Mace repo, uh, and you can just scroll down. So this is the main branch. You can scroll down, and there are two things that I would like to mention there. First, there are the tutorials. So if you click on tutorial, you have free tutorials there that are collab tutorials, and you can click on them, and they are very didactic. So you can go over them at your own pace. So the first two ones are basically the basic of using Mace, and the other one is a bit of a dive in the theory. And it basically connects what I've said in the equations to the code actually. So it can be useful if you want more to understand the theory a bit more. And the other thing that I wanted to show is the discussion section. So if you have any questions, you can click on the discussion here and open a new discussion, and you will see that it's very active. We are trying to answer as much the fastest possible any of your questions. So if you are using Mace and you don't understand something, or you have surprising results, like, please create a new discussion. If it's not a bug, don't create an issue, just create a discussion, and then we will help you. And if you want to share something that you don't want to share publicly, you can just email me, and you have my email at the very bottom here. Um, okay, and I will just go quickly about. I think I won't have time to really go over the tutorial, but I just want to present them to you. So let me go there. Yes. So the first tutorial uh, is really a big introduction to the basic of how to get started with potentials, and it's actually more general than Mace, and it starts with how to collect data. So basically, the spirit of this tutorial is you want to do potential for electrolytes, and you would like to be able to simulate these electrolytes to do battery down the line. And how do you do that? And we start by understanding how to collect data, understanding how to visualize the data. It's very important to start by having I would say, a great but even expert understanding of your data before fitting the potential, because really the model is as good as your data. So it's very important that you start by taking the data very seriously. And so here it goes over that. We use in order for that to be able to run on the notebook, we are using just a simple XTB as the target, and we go over one of the essential thing of Mace, and I think one of the most confusing one is how to take the reference energies, which are these E zeros. So usually we are not fitting the full total energy, because this is a very large quantity. It can be 1,000 of EVs depending on your code. So we are fitting the atomization energy, which is your total energy minus the sum of the energy of the isolated molecule, the energy, isolated atom. And so this is the standard way to do that, and you need to have these E zeros from your DFT, but you can also use the average E zeros that try to estimate these E zeros based on a linear fit. Uh, I always recommend, if you can do it, to use your own E zeros. I think it's the safest. Um, and then Here, I've written a bit of section on the hyperparameter of maze. So if you want to train from scratch, you can basically select if you want to have a fast maze, a medium maze, or a more accurate and larger maze. And I usually always recommend to follow the recommended values that I've written here for your first fit. And then if the fit is not accurate enough, move to a larger model. And if the fit is not fast enough during MD, then move to a smaller but faster model. And the way to select that, I think, are the two parameters you need to, I mean, the three parameters you need to have in mind are the number of channels. So this is basically selecting the width of the model, and the standard is 128. I recommend not to change that, except if you want a faster model, then you can go to 64. The symmetry of the message. So usually this is L equal 1, so this is the standard one. And also I recommend you start from that. And if you want a faster model, you can go to max L equal 0. And if you want a more accurate model, you can go to max L equal 2. Obviously, changing its parameter will affect a lot the speed. So it's about a factor of 2 to 3 for each one. So L0 is 3 times faster than L1, and then L1 is about 3 times. I would say 1.5 to 3, depends on the system. Um, and then the cutoff, which I think is the most system dependent parameter here. So you have systems where you have like large atoms, you know that you need a 7 angstrom cutoff. And then you have systems where you have short bonds, and then you can go to 5 angstrom. I recommend that you basically stay in the range of 4 angstrom to 7 angstrom. I highly recommend not going larger than 7 angstrom, and but especially not smaller than 4 angstrom. Uh, Even if from the physics you think that 3 angstrom is enough, usually it produces much worse models. Um, yes, so then here I go about how to you do the fitting of the model. So uh, let me go now to my own local page. Uh, if you, yes, one sec. Yeah. So this is the second tutorial that that I'm running locally, and this will go about. So the first tutorial was talking mostly about just training from scratch and doing a bit of MD. And then this tutorial is talking about doing a bit of iterative training. So this is the iterative loop that I discussed earlier, where you train on an initial database, and then you do some simulation, and then you train on some of the evaluated point of your simulation and go again to get new generation of models. And the reason why I want to show that now is because here you have the command to use the maze run train. So this is the command that you need to use if you want to train your own maze model. And here you see this section is selecting the hyperparameters. So here I've made a super small model because it's running on my laptop, so I don't want to take too much time. Then here you have the basic of, so you need to name your experiments, the folders to save the model, the logging of the metrics of the model, your checkpoints. Uh, that's the place where you need to point to your databases. So Mace has a few ways to load data, but I think the easiest one is the XYZ files of ASC. So you have the training, the validation, and the test set. The easier here, it's average, or you can put the true zeros of your DFT. And then the most important thing, and I think about 20% of the issues on Mace are related to that, are the keys. So the keys are basically the way to tell your model where to search. What is the name of the properties to fit to in your file? So you cannot know in advance. So you need to tell it. And it's also extremely important. So usually when you write your XYZ file, ASC writes to keys that are called energies and forces, energy and forces. And actually, this is very unsafe because ASC has updated itself, and no, you cannot read that safely. So the first thing you should do is rename these keys to a proper name. Like here it's energy XTB, but you can do like ref energy, energy DFT, and forces DFT. So go in your XYZ file, rename them, and then give them to Mace. Because if you don't give them to Mace, it will just not fit anything. Um so actually, this is CPUs of the device, the batch size, because we are using stochastic gradient descent. So you are going to optimize your model by looking at the gradient within a given batch. And then when you train, so I can try to run that here. And you see when it trains, so it has a bunch of header before tracing training, and this header tells you different thing about what is going to happen now. So it tells you the keys that you're using. So make sure to check this line to make sure that it's reading the correct keys that is in your data. It's also here saying what properties it has found in your dataset. So here it has found 18 energies for the training state, 18 energies for the validation set, and 1,000 energies for the test set. So do make sure if the energy is 0 and you have energies there, it's probably a problem with the keys. It also tells you your E0s. It also the basic hypers of your model. Make sure that when you create a discussion on an issue, you also post these log files because that helps me. Some of the optimization um, informations, and then the training happens. So you see here, it's training. So it has already finished training. So this is a very small model, so it won't be super accurate. Uh, but after the end of training, so this is the metrics that you need to check when you're training, if the training is improving. And after the training, it will evaluate the test set. So this is the validation set, and then you have a held out test set that you need to evaluate just at the end. And at the end, it will print these tables with the metrics on the test set, and it will save the models at a given path. So after it has done the training, it has trained the model, we can run some MD. So here we are doing some MD of the electrolytes, and here you're seeing I'm doing some plot of the energies and the forces and the temperature, and I mean here it's only on my CPU, so it's not that fast. But if you evaluate on the GPU, it will be much faster. And the way to do the MD is to use the maze calculator. So you can go at your own pace. And so before finishing, I would like to also go about the fine tuning. Uh, so let's say you have your foundation model. So here it's Maze MP. So you can import the foundation model. And then if you do that, you will have out of the box a calculator that you can run MD with out of the box, uh, and without training. And if it's not accurate enough, you can fine tune it. And the way to fine tune it is with the same interface as before. So you still use Maze run train, but you just need to specify a foundation model too. So if you just specify the foundation model here, either you give it the name, so small, medium, or large, and if it's a custom foundation model or a one you've downloaded elsewhere, you need to put uh, uh, the pass to the model here. And the your training fine tuning file, extra, and this will do the naive fine tuning. So starting from the foundation model, it will do the naive fine tuning, and you can also do the multi-head fine tuning by just doing uh, equal true, and this will launch the multi-head fine tuning where it will also do a replay. For the multi-head fine tuning, you can also give a replay file. So you can give either you use the internal default that we have to select the replay, or you can also give it the replay file. And for that, so this is the last thing I want to show on the documentation. Okay, now. So if you go to the Maze documentation, so you just have to go to the Maze repo here, and then you click on the documentation. Here you have a user guide, so you can go on the troubleshooting. So if you see that some things are wrong, I've put here all of the standard mistakes that you can do as a beginner. And then if you go to the fine tuning here, I've done a bit of explanation on the fine tuning. And if you go on the multi-head, I'll also explain exactly how you need to go about to do the replay and do the right fine tuning. So do read the documentation. Yeah, with that, I think I will finish there and pass it to Venkat. And thank you very much for your attention.
Right. Thanks a lot, Ilyes. That was actually really great. Certainly much better than what I would have done to give such an overview. So right. So Ilyes has very nicely discussed what we're supposed has very nicely discussed machine learning interatomic potentials. So hopefully by following what he has said and his tutorials, you can train your models. I want to go and talk about the next stage, which is actually applying these models for materials modeling. And the broad theme that I'm going to touch upon is just modeling materials at finite temperature. And just to make sure everybody's on the same page, just going to briefly recall a couple of equations that if the total Hamiltonian of your system can be written in the following way, where red depicts the terms for the nuclear degrees of freedom and blue is for the electronic degrees of freedom. Uh, then what you typically do in your simulations is something called a Born-Oppenheimer approximation, where you just separate the electronic and nuclear terms, and you take all of these electronic terms and you actually do some sort of an ensemble average over the electronic degrees of freedom. So as a result, you get this Hamiltonian, which is just a function of the nuclear positions. And what Ilyes had talked about is really being able to approximate this so-called Born-Oppenheimer potential energy surface. But once you get that, you realize that there is a second step you need to do, especially if you want to compute observables, which is a key to comparing with experiments or doing real-world modeling, right? So there's also the second half of the quantum mechanical problem that one needs to cater to really be able to perform materials modeling. So I'm going to just touch a bit upon uh, some development software and code and how actually you use these in the world where the bottom and higher potential is approximated by MLIPs, right? So again, this is similar and different from the plot that Ilyes had, which was mainly focusing on uh, the level of theory with force fields all the way up to being able to do exact quantum chemistry. And arguably, I would say that we are at a stage with MLIPs that for a lot of systems, we can use density functional theory and have inexpensive models, right? But if you think about doing any calculation or computing an observable, uh, you often need to do some sort of sampling. Uh, so just to give a very simple example, this is the expression of the Helmholtz free energy of the system, which basically is a proxy to how stable the system is at constant volume and temperature conditions. And if I were to assume that my nuclei are classical, I would get the following expression where the first term is the free energy of the center of mass of the system. It's a trivial term. Then you have an ideal gas term, and all the non-ideal behavior is actually in this configurational space integral. So Q here is the position, and you have to take an integral over the entire configurational space. And the points where the energy is low enough such that this exponential contributes are the relevant regions. And since all observables can be actually estimated as a derivative of the free energy, uh, you kind of understand that it's not just sufficient to do one single point calculation. You often have to have an ensemble of points which correspond to the configurations which would be visited at finite thermodynamic conditions and do a Boltzmann average across that, right? So that way you can actually construct another hierarchy of methods on how you should be doing your sampling. And arguably the simplest way is to not do any sampling and say, well, I've got my minimum energy structure, which I can get from optimizing, doing a geometry optimization. And at low temperatures, when I assume that thermal motion is not happening, that's representative. That's your lowest level of sampling. The next stage would be to say, okay, I can also compute the Hessian of my system through a harmonic approximation. And from that, I at least know what is the curvature. And within a harmonic approximation, I can approximate this integral. And beyond the harmonic approximation would be incorporating anharmonicity, which is really key to doing materials modeling at finite thermodynamic conditions. And the question is, how do we actually go beyond simple static and harmonic approximations, right? And I will basically be touching upon the molecular dynamics approach and its extension to quantum nuclei, which is path integral molecular dynamics. And I want to focus more on the code side of things. How does actually one think about writing code which allows you to do sampling when you have total energies and forces calculated at a high level of theory? So let's look at the just the pseudocode, uh, a very blocky way of thinking about an electronic structure problem, where you have an input block where you're providing the positions of all atoms, you provide the unit cell, and you provide the identities of all atoms, which are given by the atomic numbers. And this kind of goes into a black box. So this could be your electronic structure code, and H here is the electronic Hamiltonian, and you can actually get all of these eigenvalues, and these eigenvalues correspond to the potential energy surface, right? And this code typically outputs this potential, but also its derivative with respect to position, which gives you forces, and the derivative with respect to the cell tensor, which can be used to compute the stress tensor on the system. Now, this is great. Well, if you were not exactly doing this and you're using MLIPs, you can just think about it that the input is exactly the same, except that now you have a universal approximator just giving you these numbers instead of actually solving the Schrodinger equation here, right? Now, if you think about the molecular dynamics algorithm, it's a bit different here, where you need the positions, you also need momenta, you need the masses, and you need as an input a potential energy surface. And inside, this is just Hamilton's equations of motion, but in reality, much more complicated things happen, and you get the updated positions and momenta, right? Now, if you were to do first principles molecular dynamics, strictly speaking, your code should have a few components. The first one would actually have to deal with solving the electronic structure problem, and then you would have to go from take the gradients that you get from the electronic structure problem and evolve your nuclei, right? So we know that this is actually a very active area of research. Sampling is also an active area of research. So you can imagine that every time somebody comes up with a new electronic structure approach, something which advances or goes beyond DFT or something, you would have to think about implementing a molecular dynamics uh, snippet into your code, right? And so every time you have a new development, it actually leads to an overhead in terms of usage of the method, because the moment you actually have a new electronic structure technique, you still have to code up all of the sampling side of the algorithms. So how about this? If you actually think about these Hamilton's equation of motion, they don't really care about where the force is coming from. They're completely agnostic to whether the forces come from a force field or they come from a fully quantum method or even a quantum computer in future. So what if you were able to completely decouple these two sides of simulations, where you have a code which just deals with evolving your positions and momenta. And the moment you have to compute any derivatives, it actually outsources this task to a different code, which actually goes on and takes, okay, so I need to compute my derivative at this position. You also pass on the identities of the atoms. And then it solves the Schrodinger equation or bypasses it using MLIPs, gets all of these gradients out and passes it back to your uh, engine, which was actually doing the dynamics, right? And the nice way of thinking about this is that you can actually have two separate codes, one which deals completely uh, with rigorous sampling approaches, which just focuses on developing newer and more advanced sampling approaches. And independently, you can have codes which try to have better MLIPs or better quality electronic structure methods. And if there is a robust interface between the two, there's no overhead of usage. Every time you have a more accurate electronic structure MLIP, you can immediately perform your sampling and actually tackle scientific problems. And this is where I want to talk about the IPI code. And this has exactly been the philosophy, which is to completely decouple force evaluations and dynamics. So IPI is a code which takes care of only evolving the nuclei, and it's written in a very general way, where the evolution of a nuclei could either be just classical dynamics, it could be enhanced sampling, it could even be harmonic, which means moving along a normal mode, it or it could be completely anharmonic, and you could be evolving the system quantally. And IPy actually outsources the problem of calculating forces to well-known codes. It has a robust interface with most electronic structure codes as well as with ASE and LAMPS, which means any MLIP, most of them would either have a Python interface or one with LAMPS you could directly use with IPy and do a lot of advanced calculations. Right. So here I want to just give you a few features of IPy. It's a Python code which has some advantages. Note the first one is that it's very easy to install. So on Hub computers, you can just do a pip install, and that's about it. This code actually can connect with most MLIPs, and you can imagine, considering it's Python, writing a quick interface is actually very easy. All you need to do is be able to compute total energies and forces, which most modern MLIPs are able to do thanks to AutoGrad. And if you can talk to ASE, then you can talk to IPy. So it incorporates a lot of advanced algorithms, not just various ensembles, which is NPT, NVT, and so on, but also enhanced sampling, replica exchange, and path integral molecular dynamics, which can also treat nuclei quantum mechanically. Also want to say that we have worked extensively on providing good documentation and a lot of examples, and there's fair amount of support on GitHub or Google groups. So if you ask a question, we usually try to respond as quickly as possible. Right. So one thing that you may have thought about is, well, I mean, it's a molecular dynamics code written in Python. If I think about biomolecular codes, which really try to focus on efficiency, they're all written in Fortran, right, or C++, and of course that's going to be very fast, you know. So the question is Python an efficiency bottleneck for materials modeling? So what we found, we actually tested this very thoroughly because we didn't want to be providing a code which actually doesn't allow you to fully use MLIPs. And what we found was that if you think about the cost of every force evaluation, then MLIPs and force fields, although they are in the same uh, ballpark of being linear scaling or nearly linear scaling, they are actually pretty disparate in terms of how long it takes. And force fields can actually take fractions of milliseconds, or if you code up a Lennard-Jones potential, it could be 10 to the power minus 8 uh, seconds per atom, right? And MLIPs are actually much more expensive than these force fields. And because of that, if you consider what is the Python bottleneck of performing molecular dynamics, you would see that yes, if you perform MD with a force field with IPy or any other Pythonic code, you would always uh, be limited by the costs of IPy. However, in all cases, we found that with MLIPs, the cost of using Python as your engine was actually negligible compared to the cost of MLIPs. And because of which we can actually get decent throughput in terms of nanoseconds per day using the IPy code with MLIPs. So I can also give you some numbers here. For instance, water is a fairly useful benchmark system. And here is just again a similar figure where I'm looking at on the x-axis the cost of one MD step, which is a total energy and force evaluation per atom. And force fields are in this category and MLIPs are somewhere around here. And for a very small box, you see that, well, actually, uh, as you reduce the size of or the cost of the force evaluation, you indeed see the efficiency plateauing. So here a dashed line shows ideal efficiency, and you see that actually for force field you are actually in this regime. But if you look at the regime of MLIPs, the scaling is quite all right. Of course, for very fast MLIPs, there is a noticeable deviation from ideal behavior. But the moment you increase your system size to something reasonable that you would probably like to do because you can afford to do bigger systems which actually correspond better to the thermodynamic limit. In that case, you see that the cost and if you look at the efficiency, it's pretty much ideal. Uh, so simply put, if you were, it's almost like there's no bottleneck from Python. And of course, if you go to even bigger system sizes, so 4096 water molecules is 10,000 atoms. And again, here you see you see that it's basically an ideal scaling. So also want to say that I wouldn't take these nanoseconds per day numbers very seriously because uh, it really depends on your HPC, the status of the code. When we did this, we actually used some Mace MP0 for certain points. And of course, we didn't have CUDA equivariance boost. And with that, actually, so long story short, you should be able to, for small system sizes, easily expect 1 to 10 nanoseconds per day. And for moderate system sizes, nanoseconds per day is the regime that you should be you should be able to get with Maze, assuming you are able to use some boost features. So the other thing is, how does it scale with multiple nodes? Of course, scaling up calculations over multiple CPUs has been done for a while, and most codes are compatible with that. So here is an example of, again, IPy being used with LAMPS, where LAMPS is actually computing the so-called deep MD MLIP. And if you keep increasing the number of CPUs, the cost of every time step keeps reducing. The cost is quite high because this was a very large box. So if you do it on one core, you can probably understand that the cost would be very high. But we get good scaling as we increase the number of CPUs. And similarly, if you look at what happens with GPUs, you can also just crank up the number of GPUs and also get good scaling. So you can actually exploit modern HPC, especially if you have access to multiple GPUs on a single card or multiple cards. Right. So at this point, I would like to give you a short demonstration and of how to actually run these simulations. And if you're interested, you can also go to this GitHub link, which has a repository. So in this case, I'm just going to switch to my browser, and I'm hoping that you all can see this. Right, so this is a very simple repository that I have created, uh, and it's called MLIPs with IPy. It uses version 3.0. And I've listed a few use cases that I thought people may be interested in because I'll also be talking about much more advanced molecular dynamics later on. But I feel like a lot of times, a lot of observables that you have to calculate can be done with rather simple molecular dynamics, right? Where all you need is good sampling. So I've just tabulated a few different types of setup. So for example, if you want to do NVE molecular dynamics, there is a directory on GitHub which allows you to do that. In the constant temperature ensemble, there are a few different cases. And again, if you are used to using ASE for your MD, these are some details that maybe uh, you may not have paid a lot of attention to, which is what exactly should be the nature of your thermostat that you want to be using. If you are using a solid, simulating a solid or a liquid, should be using the same thermostat. If not, what are the ideal parameters? If you have no idea, or if you have an interface and you have no idea what thermostat should you use, is there some sort of a universal thermostat which can give you good sampling? All of these are different use cases here. So I've also included what this case could be useful for. Uh, so for example, the first one is NVT for dynamics, where so the kind of thermostat that you should be using should not be perturbing, shouldn't be too aggressive and perturbing the dynamics of the system. So here I suggested using a global thermostat, and some of the exact values are also in there. Uh, if you want to do solids or model systems, Langevin thermostat is usually a good bet. If you want to do liquids, I would not recommend using a Langevin thermostat. You should instead be using the stochastic velocity rescaling thermostat. And again, the inputs are here. And again, if you have no idea what to use, you're just looking for best possible sampling, there are some generalized Langevin equation thermostats here that you can use. And again, this kind of shows or highlights some of the advantages of using IPy for your sampling, where we kind of empower the user. So if you really want to do more advanced MD and you really know what you're doing, you can actually set up rather complex simulations. Just to go to the NVE, I want to just show you the input file for IPy, and this is what it looks like. So here, the first block of the input file is the output block, which allows you to determine what exactly do you want to print out and how often. So if there are any properties like the kinetic energy, the potential energy, the pressure. You also want to be monitoring the conserved quantity, which tells you whether your MD is stable or not, as well as the temperature. And similarly, you can print out the positions or velocities, momenta, and we can also print everything out in standard ASE format, which is the extended XYZ. So if that's the file format you're comfortable with, or you want to use later on, you just specify format is equal to ASE. If you are from the biomolecular community, you want to use PDBs, you can just put format is equal to PDB, and it's all good as well. Some of the other things I want to touch upon are the initialization block, which again requires an XYZ file. It could be a PDB file, but if this is the ASC formatted XYZ file, which is also known as the extended XYZ, then you just have to provide this. And velocities, if again, you can specify the units in which you want to thermalize the initial velocities. And here comes the motion part of which is, in this case, it's you want to do dynamics, and the type of dynamics is NVE. And as you might understand, the only thing you need to specify for NVE dynamics is the time step. And here is what you can set this up. So for molecular systems, I recommend using a half of femtosecond time step, but for ionic systems, you can probably go 1 or 2 femtoseconds depending on what system. And there's also a block for the ensemble, and in this case, it's an NVT ensemble where the initialization already fixes your N. Sorry, this is an NVE ensemble. So the initialization already fixes the volume and the number of particles. So in this case, there is an ensemble temperature, but it won't be used in the simulation because this is NVE. Right. So I also want to show you how actually you can run these simulations. It's actually quite straightforward. And here there is some documentation on just a few easy steps on how you can do this. So I'm again assuming you can see my terminal. So I want to preface this that I'm using a MacBook Air which has 2 processors in total, and it doesn't have a GPU. So everything is going to be slow, but things on a proper computer are going to be fast. So right. So you can again take a look at the input file on your favorite text editor, and everything is here. The number of steps are here. The one interesting thing here is how do you specify how to calculate forces, and that is done through this so-called FF socket. So it's called a socket because IPy is based on a server-client interface, where IPy is the server and the force providers are clients, and they have to connect through IPy. So through the so-called socket. And the only thing you need to specify if here is the address of the socket, which in this case is just the name of a file, right? So, and what you need separately is a run asc.py file. So this is what you do. You use your ASC read files. You can import the Maze MP default model, or you can also use a model that you've just trained from Ilyes's presentation and just include a path here. And after that, this host, which is driver here, has to be same as what was specified before. And ASC provides this socket client to be able to connect with servers. So that's all that you need to do. And right. So again, I mentioned that IPy is basically a way to just connect with it decouples the two things. So so the way you actually run a simulation with IPy is that you have to run both IPy and the force provider separately. So here is IPy. This is the how you execute an IPy code, and it reads the input file. It says, well, if the initialization is ready, and it also says that created Unix socket with address driver, started the pooling thread with main loop. So at this stage, IPy has done all the initialization, and it is at the stage where it's just waiting for a force evaluator to connect with IPy. And then as soon as it connects, it will pass the positions to the force provider. The force provider will do the calculation and pass them back on. So if you just run this Python file, which actually implements the maze calculator, that's actually about it. Now handshaking has happened. IPy has connected with ASE, and it's sending positions, cells, and the atomic identities to ASE, and the forces are being evaluated, and these forces are being passed back on to IPy. So so if I actually close, or if I just cancel, if I do Control C and cancel my run ASE script, you see that at this point IPy says that client died or got unresponsive, removing from list. So this doesn't mean that your simulation has crashed. In fact, if you do this, you can see that IPy is still running. It's just that it's still waiting for a client to connect, right? So if I run this run asc.py again, IPy is actually going to resume exactly from where it stopped. And yeah, you're back to step 13 probably. And yeah, back to step 13. Yeah, so the dynamics is just going to continue. So it again shows how the server client interface works, right? And if you want to, this is just a very interactive way of showing you how it works. But if you want to write a script which just does it on its own, you can do something like this. You first run IPy, pipe the output in a file. If you do sleep 30, just make sure there's enough time for IPy to create a socket, and then you run this. So of course, this 30 could be replaced by 5 as well. But if you have a very large system, then it's just recommended, or sometimes clusters can be slow, it's just recommended to use this value, and you won't have problems, right? Right, so this was IPy. And again, I've canceled this, and just want to say that if you create a file called exit in the directory, IPy does a soft exit, which means that it creates a restart file. So if you want to restart your simulation, you can use this file. And you can actually take a look at the restart file. It is basically the same as the input.xyz file, except it contains all the details of the state of the system. Even the random number generator, which is somewhere around here, just to make sure that if you had one long simulation versus two short, even for stochastic simulations, it would give you the same result. So if you want to restart the simulation, you again do IPy restart, because restart is your new input file, and you run this. And right. Right. Again, this is my MacBook Air with 2 cores, which are probably already being used by Zoom, and there's no GPU. So I'm sure when you do this on your cluster, you'll see that everything is very fast. Again, if I do touch exit, everything quits properly. There is a new restart file. The old one has been backed up, so you don't lose previous information and so on. Right. So again, this was NVE. Now we can look at NVT. So the only major difference is that it's now the dynamic says NVT, so you also have to specify a thermostat here. And of course, this ensemble temperature now is actually used up. And this thermostat, I'm using the so-called SVR, which is stochastic velocity rescaling. It's a global thermostat, which means that it changes the velocities of the full system in one step. So they are just rescaled in a random way. And this is good for recovering dynamics, because if you use a Langevin thermostat, every atom's velocities will be change in a random way, right? So that will disrupt dynamics. And the other thing you can consider is how often do you want to print the stride for your dynamical property. For example, when I do spectroscopy, I usually use 1 femtosecond or 2 femtoseconds print out my position so that I can do my analysis and even get the response of high frequency modes, right? So I also want to show you another thermostat, which is called the GLE thermostat, which is generalized Langevin equation. So this is what it looks like. And I know it looks scary, but if you are having cases where if you have a solid liquid interface, a liquid gas interface, and you see that, okay, my temperatures are different because there's basically no transfer of energy between the two systems, you can just use a GLE thermostat. It's going to give you optimal sampling. And you don't really have to think about what kind of thermostat you use. Of course, you shouldn't use this if you want to study dynamics. This is just for structural properties or equilibrium properties. If you want to study dynamics, I would say first perform a simulation in the NVT ensemble with this, and then the snapshots that you get, you can do NVE or NVT for dynamics, or NVT with the SVR, stochastic velocity rescaling thermostat. A few other cases are NPT simulations. These are quite important because experiments are often done at constant pressure. Even solids have a response to finite pressure. And here you have, so again, it's very simple. Only thing that changes is that the dynamics is now NPT. So you also have to include a barostat, and the thermostat remains, and your time step. You also have to include a pressure in your ensemble, and you can use the units that you like. Uh, Another important thing to note, if you study the equations of the barostat is a fictitious particle which almost gives a momentum to the unit cell of the system. So it should also have a thermostat. And so when you specify a barostat, you also have to specify a thermostat just for the piston in some sense. And so you can do this. I've also included some notes on how should you be selecting these quantities and what are the ideal values. So of course, if you have questions, you can ask me. There are some other cases which is like flexible NPT, which means if you want to allow all the degrees of freedom of your unit cell to change. For example, if you do want to study the phase transition of a perovskite, you will have to actually do a flexible NPT. If you do isotropic NPT, you will probably get the wrong phase transition temperature. And I mean, idea is simple. You just set barostat mode flexible, nothing else changes. And again, there are some notes on how to do these. So to my understanding, with simple Python interfaces like ASE, you maybe there's a new version now, but I think NPT is probably not very well documented, or the algorithms that I use are not rigorous, which are like they are not rigorous algorithms which give you the exact ensemble. So these are your, if you really want to be sure about your sampling, these are the algorithms you could use. There are a few other examples. I won't get into that now. Instead, I can actually just show you a few more advanced use cases through just some through just some images from figures, and do some discussion. And of course, you're welcome to try those more advanced cases yourself and tell me whether you find them useful or not. So one of the things is often you have to compute properties at various temperatures, right? And look at the temperature dependence. So of course, if I ask you to tell me what system this is, you will not be able to tell, because even though every temperature has been run for 1 nanosecond, the density hasn't equilibrated. This is liquid water, and it should have a temperature of maximum density at around 4 degrees centigrade. But often you see that sampling it's actually hard to get very efficient sampling, and often you need to run for tens of nanoseconds, right? But there is actually a very well-known enhanced sampling algorithm called replica exchange or parallel tempering, which can actually exploit good sampling at high temperatures and use some of these structures uh, to enhance the sampling at low temperatures. So if I just perform the same simulation with replica exchange molecular dynamics, which in IPy is just one line of specification, uh, then you get something like this. So mind you, this was 1 nanosecond for every temperature. Here is, I think, a few hundred picoseconds for every temperature. And you can see that with very short simulations, you can actually get converged statistics. And at this point, I could probably show you what an REMD input looks like in IPy. So IPy also has the feature where you can run multiple temperatures in the same simulation. Every temperature will evolve independently. And to do replica exchange, you just have to include this flag here. And stride one means that at every step, it will try to swap position between various temperatures. And of course, REMD can also be done in more complicated ensembles like NPT, and you can even exchange across various pressures if you think that at some pressures you have better sampling, and then so you can get really good results. So I think this is quite important because even if you have a very fast potential, if your sampling is slow, you can't get reliable results. And again, it shows that with good sampling, you can actually get away with a very few points or very short simulations, and more confident results, of course. So enhanced sampling is not just about replica exchange, but IPy also has an interface with a software called Plumed, with which you can actually do enhanced sampling along collective variables or order parameters. So this is one case where we were studying the absorption of a gas inside a porous organic solid, which means if you have so in this case, it's actually quite interesting. We use a mixture of high H2 and D2. And because of quantum nuclear effects, H2 is actually going to be slightly larger than D2. So if you tune the size of your porous solid very specifically, it will be uh, large enough that H2 can pass, large enough that D2 can pass and small enough that H2 can pass. And of course, if you just run MD, you will never see this event because the entire transport of an H2 through this pore is actually a rare event, right? So you have to be able to bias your simulation along this order parameter. And of course, because IPy has an interface with Plume, we can directly run these simulations and also include quantum nuclear effects. And actually, we could see that the barrier was different, and from those barriers, we could also estimate what is the selectivity for absorption and so on. But again, these kinds of enhanced sampling algorithms are quite general, and you can do all sorts of phase transitions or chemical reactions that you're interested in. Another thing that we have in IPy is making it more customized to machine learning potential. So there is a functionality to be able to do committee neural networks. So if you provide n uh, n neural networks, it will actually compute the mean. But what it will also do is that it will also pass on the uncertainties in in forces or energies or stresses. And with that, you can do some interesting things. For example, you can construct a simulation in which your potential comprises of a baseline which you know is going to work, and then you have this V delta, which is actually which is a committee, but there is a prefactor here. And if you study this prefactor carefully, what it says is that if my uncertainty is greater than sigma b, then this will basically become zero. So your simulation will be done purely by a baseline. And if uh, this is if this uncertainty is low, then your potential will actually just be a correction to this baseline. And the advantage here is that, for example, in this simulation, we're just plotting at various temperatures uh, this weight W, which is basically this term. And you see that at low temperatures, this was just some molecules where we used tight binding, density functional tight binding as a baseline, and our MLIPs were delta models. So when this weight is basically one, your total potential is the baseline plus the delta correction. So you can actually do regular sampling. But there are instances where the simulation led to exploration of regions which were outside the training set. And in that case, the simulation did not explode. It just noted that the weight was low, due to which it was able to reduce the magnitude of this delta correction, which would have been erroneous because its uncertainty would have been high, right? So with this, we could actually go even all the way up to very high temperatures, and we could even see molecules reacting and combustion of molecules in this case. And all of these simulations were completely stable just because you were using these uncertainties to drive dynamics in a sensible way. Of course, uh, I wouldn't be using the outcome of the simulation to infer anything, but I could use this to, for example, retrain my model or fine tune my model. And then, it just makes life much easier where you have stable simulations which can actually explore regions which are not in your training set, instead of having to carefully check every time. And of course, you're welcome to implement if you have smart ideas on how to better exploit these uncertainties. It's all possible to just use them in IPI. Another thing we can do is not just pass energies and forces, but from MLIPs, you can also pass the electric fields and the dielectric response of the system. So if you also learn the dipole moment, and in PyTorch, if you use mace, you will also have access to its derivative. That is also something you can pass through IPy. And in this case, this is a very simple example where you have a time-dependent external electric field given by this wave packet, where on the right-hand side is the electric field magnitude that you're seeing. And interestingly, for a water molecule, you see that you can actually print out what are the various energies along the three different normal modes. And you see that this electric field couples only to one of the normal modes, and the energy goes into one of these modes. So this could be, you could be thinking of it as like shining a laser on a system, right? And seeing what is the response. So these things are, again, fairly complicated setups, which require a tight integration of uh, the machine learning potential or electronic structure code with dynamics. And all of these are possible in a very transparent way. And of course, you can do something much more advanced than this, than this simple demonstration. And again, talking about dielectric responses, a lot of the work, a lot of spectroscopy also depends on Born effective charges, dipole moments, polarizability tensors, and so on. And demonstrations are available on how you can pass these through IPy, so that you just print out these as your trajectory, and then perform dynamics. You can also include, so for example, this is just the case of IR and Raman for liquid water, where you see that if you just do standard MD, which is in dashed lines, you would get shifted results with respect to the experiment, or if you include quantum nuclear effects, you get the right line positions. And these are also available in IPy. A demonstration is available. If you're really adventurous and want to understand whether a single peak is one peak or is this a combination of many peaks, you can do high dimensional spectroscopy here. And there's also a very nice demonstration available on how to do 2D IR, for example. And if you also want to include quantum effects, that's also possible in this case. Again, I mean, so if you go to the GitHub repository of IPy, you'll see many things. So here is this, and mainly two things that I want to show you. One of them is the examples directory, where we have actually separated the examples with respect to how to run with different clients, but also with respect to different features. And so there's really a lot of documentation and examples available, which you can, which really allows you to perform advanced setups, and there are HPC scripts as well. If you want to do it on a single node, multiple node, if you use Slurm, if you use Torque or something, PBS, you can just write to me, I can share something with you. And there are also demonstrations, and demonstrations are meant to be much more, it just walks you through the entire thing. For example, if you want to do spectroscopy, there are all of these steps that you can follow to be able to get the final spectra. There's a few different things like solid liquid free energies with uncertainties, 2D IR, just standard MD, and phase transitions for para-hydrogen, a very simple case. There's also the website of IPy, which is ipycode.org. Of course, thanks to here, I mean, there's a lot of information available. If you, for example, if you just want to look at the documentation of IPy, it's there. And what we also have here is a troubleshooting, frequently asked questions and troubleshooting sections. If you have errors, we comprehensively provide you with ideas to really help you out, help you set up your simulations. Of course, if you use these examples, hopefully you won't have these errors. there's also a Google group here. So if you have some problem, you can just write to us here. It's called IPy users, and this information is also available on the website, and you can just post your questions here. Again, we try our best to respond or point to the documentation wherever available. And then there's something called the atomistic cookbook, which is a very interactive way. It shows you the recipe of doing something. So for example, if you do this group by topics, if you want to do constant temperature MD, it really goes through all of these steps with a proper documentation and tutorial. And if you really want to try this on your laptops or on your computers, you can just download the recipes. It even has a Conda environment, which allows you to set up, so you don't have to install lamps or CP2K or something like that. It will just provide you with everything. Right. And with this, actually, I'm at the end. So